Hello. Can everybody hear me okay? The back. Okay. Welcome. Thank you very much for coming to my talk, for sticking around for this long. I hope you had a great conference. I think I'm recognizing some of your faces. I think maybe I saw some of you yesterday at lunch, the diversity luncheon. So it's great to see you again. To those of you who didn't hear me speak about my project yesterday, which I was able to shoehorn into a talk about diversity, I am now going to talk about it, in more detail. So the talk today is visual diagnostics for more informed machine learning, and here's some ways to find me. So like Mandy said, my name is Rebecca Bilbro. You can tweet at me if you have questions. I'll tweet out the slides after the talk. My day job is at ByteCubed, and then my passion project is working with district data labs and doing open source development. So I'll tell you a little bit about my work at ByteCubed, since they were, very kind to kind of sponsor my attendance to this conference. It's a small tech company in Arlington, and I lead a team of data scientists who are using a bunch of different kinds of machine learning tools to basically try to do kind of like next generation business analytics. We are hiring. If you are interested, come and talk to me. It's a very quick-paced place to work, and it's a fun group. So come chat with me if you are curious to hear more about that. But I also want to talk a little bit about kind of how I even ended up here. So I started out as a child, as probably many of you did. But in terms of machine learning, my path to machine learning was sort of circuitous. So basically the first question, when you talk to machine learning people, I feel like the first question they ask you is, do you have a PhD? And I do. I have a PhD, but it is not in machine learning. So I studied math, and then I studied technical communication and information visualization, and then, kind of meandered a lot and ended up in data science, and kind of just fell in love with machine learning. And so I think part of the reason is because Python, as I'm sure many of you have noticed, Python makes machine learning so easy, like scarily easy, right? It's like 4 lines of code, and you are machine learning already. So that is exciting when you're getting started. You get to wield all of this power so quickly. You don't even have to be that good at programming, to be honest. So I sort of wanted to go through, just to convince you, if you aren't already convinced, kind of how quick you can sort of get there, from sort of soup to nuts, getting going with machine learning in Python. So basically, you have to get some data, you have to prepare it, the wrangling part. You need to pick an algorithm, a model. You have to instantiate and fit that model. You should validate it because you're a nice person. And then you deploy it, right? So it's really just as simple as that. And so to go through in a little bit more detail kind of what this looks like in practice is, when I was getting started, and I think a lot of people sort of start here, right? Because you go and there's all of this like curated data for you. It's like even better than curated. It's like manicured data. It's like an English garden of beautiful little data sets all in a row. And it's very clean. It's like ready to use. There's information about, what the attributes are, what the features are. It sometimes gives you advice about which model to even use. There's publications associated with the data sets. So, you kind of get started with one of these data sets probably. If you don't know what model to pick, you ask the internet. And all of the very opinionated people of the internet eagerly, sort of answer your question about what model you should be using, because they have a favorite. And then, like I said, it's like 4 lines of code in scikit-learn, and you're going already. So you import your model, you instantiate it, you call fit, and then you call predict, and that's it. Then like I said, we're good people. We know we need to validate our models. So scikit-learn comes with all of the metrics that you need. So if you're doing regression, you're looking for the mean squared error and the R-squared score. If you're doing classification, maybe you're looking for your F1, or you just run a classification report and it gives you F1 and recall and precision. And then, maybe you didn't do as well as you thought. So you use scikit-learn's grid search tool to kind of like grope around for better hyperparameters. And hopefully you get your scores up. And so you kind of maybe iterate through this a little bit. Then you can deploy it by just, the model that you've fit already. You use it to predict on a new X, your new input. And then you have to figure out how to put it into a pipeline, and it looks kind of this. And then you can deploy it, and basically you're done. And you know how to do machine learning now, and that's really all you have to do. So I think probably, like, as I'm telling this sort of version of the narrative, I'm seeing, recognition in your eyes, and I'm not sure, this isn't like a super slick version of the story, but I gather that probably a lot of the self-taught machine learning practitioners in the room probably figured it out this way. And I'm not going to make you raise your hand, but I just can tell from how you're looking at me that a lot of you got started this way, right? So this is how I got started too. I'm raising my hand. But the thing is at some point after doing this a couple of times, I started sort of feeling like this sick feeling in my stomach. Like at night I would look up at the ceiling and kind of feel like this terror that I was wielding all of this power, and I had no idea what I was really doing. And as a former math major, I sort of felt like maybe I should understand a little bit better what's happening under the hood here, even though you don't really have to kind of just get going. Maybe kind of to go to the next level, you do need to have a little bit better of a sense. And I think that this kind of took me on a whole different journey from the first version. And really, I think what I've learned is that machine learning is easy, but informed machine learning is hard. And I'm not here to offer you the silver bullet for that, because it doesn't exist. People who are really good at machine learning, people who went to school to study machine learning, studied it for a long time. They invested a long time learning how to do this, and you're not going to figure that out on your own overnight. There's no magic thing that you can install that will kind of do all the thinking for you. There's no package that you can outsource the thinking to. No matter how slick the graphical interface is, it's not going to do the thinking for you. It's not going to build your intuition. So we just need to sort of acknowledge that informed machine learning is going to be hard, right? On the other hand, we want to be informed, right? Like, we can't just give up and say, all right, I'll just do dumb machine learning then. We want to be informed because machine learning applications and machine learning is, increasingly driving a lot of decision making, more and more decision making. Everything from sort of wartime operations to like dating sites. So really like a full range of kind of things are being driven and being informed by machine learning applications, and we want to be involved in that, right? That's the tech that we want to build or optimize. Or spin off of. And so we want to make sure that we are pointing people towards the right things, whether it's the right bad guys or the right, special person. We want to make sure that we are, making good machine learning decisions. So, does anybody recognize this image? Who knows what this is? Like the 3 people who have been in my class before all know the answer. So what is it?
Anscombe's quartet.
Yeah, Anscombe's quartet. So the lesson, I think, for me, of Anscombe's quartet, so Anscombe's quartet, if you don't know, it's 4 synthetic data sets that are meant to illustrate that, even if you end up with data sets that have very similar kind of statistical behavior, they can be very different in practice, and maybe you can't actually see how different they are until you visualize them. And so here's a terrific example of that. These are 4 data sets that basically, if you did like, dot describe, if you loaded them into a pandas data frame and you said dot describe on all 4 of these, you would get basically the same numbers on all of them. And so that might lead you to say like, oh, well then I'll use the same model to predict the behavior of all 4 data sets. You would not do so well using the same model on all 4 of these data sets, right? They have extremely different behavior. But you can't kind of tell that until you see them, right? So when I started thinking about this more, I started feeling like the solution to the informed machine learning is hard problem is maybe building in more visualization. And I have this sort of concept of doing machine learning in color. Basically, what I would like to show you now is kind of what I think of as the yellow brick road. So it's a sequence, a set of kind of visualization, diagnostics, visual diagnostics that you can deploy at multiple phases of the machine learning pipeline to help you kind of start to build intuition, start to say, this is what's happening, this is what's going wrong, this is why this is going wrong, so that you can make better decisions and iterate faster and smarter. So in order to kind of get there, though, I just want to use this term. So I'm going to explain that the model selection triple basically is this concept that machine learning is, yes, it's definitely about selecting the right model. Thank you, Stack Overflow. But it's also about kind of feature selection and feature analysis, and also about hyperparameter tuning. So those 3 things are sort of critical. And so the feature analysis part is where you're starting to kind of figure out where your signal is, what some of the problems might be, what's going to inform your model, what's going to be predictive, what's not going to be predictive. Model selection, ends up being about, picking the one model that you're really good at tuning and then only ever using that one. Just kidding. Sorry. That's what Stack Overflow will tell you. So, it's about kind of figuring out what algorithm sort of best captures the specific behavior of your specific data set, meaning that it's not going to be the same model every time. And then hyperparameter tuning. So hyperparameters are the parameters that, so scikit-learn has default hyperparameters for all of their models, and they'll set the alpha for you, they'll set the gamma, the C. But if you're not doing great and you use grid search, what's happening in grid search is it's trying to optimize the hyperparameters within some set search space so that you can improve your model performance. So essentially, the yellow brick road is going to take us through the model selection triple. So here are some kind of examples. So that first part, the visual feature analysis, getting started with box plots is a really terrific kind of starting point. So right away, you can see that there are two of our input features that are way out of scale with the other features. So that gives us a lot of information. It takes an instant to look at this, and already like maybe you want to do some sort of standardization or normalization of your input. Histograms are also terrifically useful. Basically here you histogram it and you're like, please be a normal distribution. And if it is, or close enough, you can sort of use a lot of the standard models. And if it's not, you might need to get a little bit creative or do some more research into kind of trying to figure out what's going on with your data. And actually, I should say there's also one that I haven't included here, which is violin plots. I'm not sure if other people use violin plots, but basically it's like the best of both worlds for box plots and histograms, because you get kind of the information that's encoded in both in a single graph. So sploms, I'm not sure if other people use these or call them this, but this is a scatter plot matrix. So we do pairwise comparisons of the features. So you take two at a time, and you pair them up and graph them, and what you're looking for is like linear relationships or quadratic relationships, or maybe you're looking for kind of how the features are distributed relative to each other, so like homoscedasticity and heteroscedasticity, which starts to get at problems like bias and variance. So you can see that really early on before you do any modeling at all. Joint plots, so basically, sometimes your splom gets a little bit big, and you need to have, something to focus down on, and that's what, a joint plot basically is. We're also getting we're getting kind of the kernel density and the Pearson coefficient with this one. I'm not sure if people use RADVIS, but RADVIS, radial visualizations, are a great way to sort of hunt for separability in classification problems. So here, the first thing that I see is I'm starting to sense that, there is some distinction between the blue dots and the orange dots. It makes me have some confidence that I'm going to be able to separate them by building some kind of classifier. Same thing with parallel coordinates. So, whereas with RADVIS, we've got our features plotted around the unit circle, and we let the features pull the data points towards them based on their normalized values. With parallel coordinates, we have the features plotted on as parallel lines here, and each line segment represents a single vector, a data point across the different attributes. And what you're looking for is, chords of color. So that says that the yellow class, there's a braid of color there, and there's maybe some braids of blue that start to make you feel like there is separability here. That you maybe can build a classifier that's going to be able to predict, yellow and blue. So for model selection. Probably some people are familiar with this image. Yes? So this is the scikit-learn kind of decision tree flow diagram called Choosing the Right Estimator. This is a terrific place to get started. I always point students to this in the beginning because it is an interactive walkthrough of kind of an interactive introduction walkthrough of scikit-learn models with this sort of decision-making process factored in. So it asks you, how much data do you have? How important, are the features? Are you trying to regress? Are you trying to classify? And so it takes you through this decision, and it ends up pointing you to a model to try. So this is a great place to get started. For people who are a little bit more experienced with scikit-learn, you know that this is a little bit out of date. It does not represent all of the models that are available in scikit-learn. In fact, it doesn't represent most of the models that are available in scikit-learn. And so you probably will quickly exhaust this and kind of be ready to go out and explore some other models. But it's a great way to get started. Also part of scikit-learn are these comparison plots. So there's the cluster comparison plot and the classifier comparison plot. So I don't see these as being things you can really deploy each time you're building a model. But I do think, if you're doing clustering, if you're doing classification, going back and looking at these plots I think is really useful, because what you do is you start to be able to visualize, how these algorithms carve up data space, and they do it very differently. And so, it's not just, when you're instantiating a model, it's not just letters, it's not just words. You want to start thinking about how is the model that I'm fitting and predicting on, how does it cut up the space, and does that make sense for the data set that I've just been visualizing using all these visual, feature analysis tools. I've been sort of playing with some other ways of kind of navigating all of the different models that are available. I think Hadley Wickham has this really great paper on removing the blindfold. I'm not sure if people, this is like a Python group, so of course you never read anything about R. But it's actually a very good paper. And one of the big concepts in his paper is this notion of models as being families, forms, and fitted models. Models is an overloaded term. So models refers, to families of models like classification, naive Bayes models. It also, refers to like the actual form of the model. So a model before it's fit, and then the fitted model, which means the model that's already been, the parameters have already been adjusted because you've called fit on it already, right? So I've, kind of been thinking about how, there are different ways to represent the models. I'd be delighted to hear, if you've kind of come up with other ways of navigating scikit-learn's models or other libraries' models. I think another kind of, another way to approach model selection is just by using all the models, which Nicole talked about in her talk yesterday. Like, why choose the model when you can just use all the models and then decide which one does the best? And this is a way to visualize how different models are performing. So instead of working really hard to pick a model in the beginning, just use a lot of models and then compare their classification heat map in the end. So this is just like kind of a traditional confusion matrix or classification report, except that it's overlaid with a heat map. So you can kind of quickly say like, okay, the darker blues are the place where I'm performing better. The lighter grays are the places where I'm performing worse. Although in the context of this one, we're doing pretty well. We don't really have, it's probably made up data. At least I generally don't do this well. I'm just going to be honest with you. So you can do something similar with like rock-awk curves. You can start to visualize how your model is performing. And what I really like about this visualization is starting to show how you can use small multiples. You can compare models. So this is comparing a linear SVM and a k-nearest neighbor classifier, and you can see that they perform differently. For regression, you can do something similar. You can compare, you can use model evaluation techniques to select the model that's doing the best. What's nice about this, so this is a prediction error plot, which is really good for assessing how regression models are doing. You can start to see not only which models are doing better, but you start to maybe see why they're doing better. And residuals is sort of just another, basically it's just another way of looking at prediction error by looking at, the residuals and then plotting. Here we've plotted the training points against the test points. So you can see kind of how the different models perform. So for visual tuning, I'll remind you of kind of where we started with hyperparameter tuning, where we're basically just using grid search and saying, search for me, figure it out, optimize it, and then just tell me the answer so I don't have to think about it. The problem with that is that in order to really do well with grid search, you already kind of have to know the search space that you're looking in, or else it's going to run for a very long time. And maybe break your computer. I think what I would sort of propose is if you're trying to figure out how to kind of explore your hyperparameters is to use something like a validation curve, where here what we're doing is we're exploring a single hyperparameter across a range of values and looking at how it impacts the training and cross-validation scores. And so what we're looking for is like kind of that optimal point where we haven't overtrained yet, but we're starting to get good cross-validation scores. Another kind of approach to this is using pairwise hyperparameter tuning. And this is what I sort of think of as like a visual grid search. So here we're looking across two hyperparameters and then looking for the places where they together result in the best performing model. So let's see. Okay, just doing a time check. So essentially, I feel like this gives you a lot. These kind of techniques, they get you pretty far in terms of starting to develop intuition around machine learning. The problem is that those things that we just deployed are spread out across a bunch of different libraries, right? So some of that is matplotlib, some of that is pandas, some of it is seaborn. It's really spread out. It's not very easy to kind of just build it into your workflow. And so what I started on was building my first open source project, which is a project called Yellowbrick. And Yellowbrick is sort of an attempt to re-implement a lot of these methods under a single API. And really the idea is that this is an API that plays very nicely with scikit-learn's API, which is amazing. I can't overstate that. Like, scikit-learn's API is terrific. And what I wanted to do was build in kind of just that added layer of visualization so that you could be exploring your features and your model performance and your hyperparameters. And you could do it all within kind of natively scikit-learn workflows. And so basically, the concept is that we've got visual transformers. Right now, in Yellowbrick, we have two sort of components that we've implemented. We've got feature evaluation and model evaluation. What you can do now is you can use Yellowbrick to do things like searching for separability. We've got our own pure matplotlib implementations of parallel coordinates and radviz. And one of the things that we'll be able to do soon is you'll actually be able to interact with the attributes, which you can't do in any of the other implementations that are available. So you'll be able to like pick up this attribute and move it to a different part. And so what that will do is if two attributes are pulling in equal and opposite directions and canceling each other out, you'll be able to flip them and quickly see, if there's actually, something interesting there. So I think that will be pretty exciting. But for now, you can plot these natively in Matplotlib. We have kind of our own color scheme. You can also do a couple of things that are harder to do in other libraries. I'm not sure if other people have explored rank 1D and rank 2D. This is kind of like a twist on the sploms. But basically, what we're doing here is looking for, for signal, right? We're looking for, informative features. And right now in Yellowbrick, you can do that in a couple of different ways using a couple of different evaluation techniques. You can evaluate your models. So here are the examples for regressors. We also have classification heat maps and rock-out curves for classifiers. And we've also got a few special things in there to kind of help you start identifying potential problems with your data. So this is a class balance report. So if you are kind of noticing, some strange performance with a classifier, you could call a class balance method and get a very quick visualization of kind of what any potential kind of imbalance problems are. So I'm happy to say that as of about an hour ago, or 30 minutes ago maybe, so we deployed Yellowbrick to the Python package index, a very, very initial version a couple months ago. We just pushed 0.3, which is an alpha, but you can pip install it now, I hope. Feel free to try it now and see if it works. But yeah, so you can actually kind of start engaging in this right away. And by the way, if you are interested in engaging with Yellowbrick, I made this plea yesterday during the diversity luncheon, but I'm very interested in recruiting testers. So if you are a visualization person and you're really, you like the visualization stuff, kind of sign up, become a tester. If you're a machine learning person, definitely sign up. If you're kind of neither and you're looking into getting involved, this is a great way to sort of start learning about how to be a more informed machine learning practitioner. If you are interested in contributing to an open source project, this is a way to become a named contributor to a library. So I'd be delighted for people to kind of get involved, and I'm very excited about this project. I think one of the things that I said yesterday that I want to kind of reiterate is that this is the sort of thing where your engagement will really inform kind of where the package goes. It's in very early days, and I think it would be very interesting to hear from you what kinds of visualization techniques you've been using, as part of your machine learning workflows, so that I can kind of know about that. We can think about it and think about how we could build those in and re-implement them, and kind of integrate those in, even if it's not Python. If you're an R user, I know there's a lot of interesting R libraries for doing visualization. So definitely, talk to me, let me know, reach out, become a tester, get involved. And, again, my name is Rebecca Bilbro. I'm delighted that you came to hear about my project, and I'm happy to take questions kind of now or, out in the hallway later, or you're welcome to tweet at me, or reach out through GitHub, or through the tester forum, which again is so it's bit.ly/YB testers. We're sort of imagining like people import Yellowbrick as YB, so YB testers for alpha testers, and that's what I got. Thanks very much.
All those pretty color schemes, those are baked in as the defaults?
Yes, so you can check out, there's a couple of different palettes that we've built. I'm just going to be honest with you and say nobody who's currently working on the project is a graphic designer. So if there are any people who are very good at colors, there's an issue specially designed for you in the backlog. I would be delighted for you to check that one out and make us some prettier colors. But basically what we're trying to do is kind of have like the, our own spin on the traditional, like, the single letter colors, that, Seaborn has and Matplotlib has, just so that it's easier for a user to deploy colors using a single letter. And we want the colors to be somewhat similar to what they'd be expecting from having used other libraries, but maybe have our own kind of twist. And if you want to make it prettier, like I will be happy to merge that in. Other questions? Mm-hmm.
So I understand it's a fairly new project, but besides the documentation, any other resources you would recommend or that are available to learn about the project?
Oh, that's a great question. I think my mic is like revolting against me. There definitely is more to learn about the project. If you can visit the District Data Labs website, so it's www.districtdatalabs.com. We have a blog, and there's a series of 3 blog posts that go through in pretty deep detail kind of the different parts of the visualization pipeline that are precursors. They were sort of part of the evolution of this project, so they give you a lot of kind of the rationale for some of the design and implementation choices that we've made. So that's a great way to kind of get like a quick and dirty introduction. And reach out, and after you've read those, reach out and ask for more, and it'll be a steady stream of I'll never leave you alone. Other questions?
Would you say a few words about District Data Labs? What is that?
I'd be delighted to. So District Data Labs is an open source collaborative. We all have day jobs. So I work at ByteCubed. I'm the lead data scientist there. So that's how I pay my mortgage and buy medicine and stuff. But District Data Labs is like my Mike didn't like that answer. It wants me to pay for things. District Data Labs is like my passion project. So there's a couple of folks here who are with District Data Labs or kind of affiliated with District Data Labs. Nicole, Alan, Tony is our founder, and I'm not sure if anyone else, I'm not seeing you. Essentially it's just a group of people who really like building things together. We get together on the weekends and at night after our kids go to bed, and we build projects, and we try to, make cool things and put it out into the world. And so sometimes that's open source Python projects. I think like for Alan and I, and Nicole and I are really interested in building where we want to develop things. Tony is really interested in kind of curating like thought leadership, and so he's put a lot of work into making sure that we publish a lot of ideas onto our blog, so you can read through code snippets and all kinds of workflows and all kinds of information on our blog, and it's all free and open. Everything we do is out there. You can go to our GitHub organization, and there's a bunch of repos that you can clone, you can spin off, you can use however you like. You're welcome to contribute or just to use it for yourself or something cool, and then let us know what you did with it, and that would be great. But yeah, we're definitely always looking for people who want to join the collaborative and work with us on projects or do blog posts. Be delighted to talk to you more about it if you want to. Other questions? Well, I think there's about 5 minutes before this doesn't like me. There's about 5 minutes before the lightning talks start, so I bet there's going to be some really good ones. So if you would like to go see those, I won't feel bad if you rush off to them. But feel free to reach out to me on Twitter or through District Data Labs or through our our test site. I hope to hear from you and see you around. Thanks very much for coming.